Good morning and good afternoon. Welcome to Mirabilis Design's webinar on Introduction to Architecture Exploration. I'm your host Deepak Shankar, and today I will be going through the basics of architecture exploration, the terminologies, what are the solution requirements, what is the depth or breadth of architecture exploration, and finally walk you through an example to show you how architecture exploration can be used in your product development or your product design flow. To start off with, architecture exploration is a pretty large or vast area of engineering design. It starts off at your conceptual or your planning phase, where you have some requirements from your customer, you have some rough architecture, which may be most likely on paper, and then you would take all of that, assemble a model, conduct a variety of trade-offs, do some optimization, functional studies, all of those to come up with something that meets your requirements, which may include technical requirements, business requirements, and also other criteria such as cost and other attributes as well. Once you're done with that, an architecture exploration flow goes to three stages. One is generates documentation that can be used either by marketing or product engineering or by testing or even sales. Second part is where it can be used to become the specification that can be built either by an internal team or an external partner. And it can be both at the semiconductor level, embedded systems, and software level. And finally, it provides a platform for starting to do early software development, field testing, integration testing, and a variety of other requirements that come along the product development flow. Now, when you look at system architecture exploration, a typical system is going to consist of three parts: communication, computation, and scheduling. Communication is your topology, your fabric, your bus, your knobs, all of those can be at a board, can be at a network, can be at a semiconductor. So for example, here, this is like a shared bus. That one is a ring, that's a network on chip. That is a complete embedded systems distributed network. These are a whole variety of devices that would exist on the system. And finally, different types of scheduling, arbitration, flow control, and a variety of other capabilities. So I could have a variety of architectures that I would want to evaluate. So for example, one of them can be where I have a multi-bus with a bridge and devices connected off of it, with each element of my system having its own scheduling. Or I can have a more centralized scheduling, which can be a combination of, in this case, I'm using some sort of a specialized proprietary fabric connecting all of them, but having a static schedule. Now the question comes up is, which architecture is better suited for application? To be able to really answer that question, there are three things that have to be considered. First and foremost is, what is the traffic and the workflow? Second is, what is really the focus? Are you trying to get lower latency, higher throughput, lower energy or lower power, or is it an overall cost? What is the decision criteria? Based on these two, you can evaluate which architecture is most suitable for an application. So for example, if you're designing, say, an SSD system, depending on whether it's going into a mobile, whether it's going into a data center, whether it's going into a desktop, your form factor, your cost, your performance, your throughput can be completely different. So for the same product, you might have different architecture requirements. Now, architecture exploration can be used across every application space. You can do it for a car network, you can do it for a rocket, you can do it for a semiconductor component like a Power 10 or Power 9 processor. You can do it for, in this case, it's a SSD drive, to a hard drive, to a camera, to flight avionics. Pretty much any application that involves electronics can use architecture exploration and really will benefit from architecture exploration. Now, architecture exploration, as you saw earlier, starts from a very, very early conceptual stage and can go down all the way through your product development flow. Now, within the architecture exploration, there are a lot of aspects. First is, as I showed you, you're putting in your inputs, requirements, and concepts to create an architecture model where you're doing very early analysis. So at this point, you're not too worried about, is it an ARM A53, or is it an Ethernet switch from Marvell, or is it a box that I'm buying from Mercury Computer or Fujitsu? Rather, you're trying to get, how does that requirements translate into an engineering problem? From there, you start moving to performance, power, optimization, and trade-offs. In this case, you're looking at failure, functional analysis, security, a variety of those kind of attributes. And at that point, you know exactly what is going to be the minimum latency or the highest throughput that I can actually achieve. At that point, you start moving into hardware-software partition, meaning that you're looking at, how do I split this data across multiple subsystems or across multiple IPs on a chip or across multiple boxes. And of course, that's where you start dividing into portions of software and hardware and start selecting different components, scheduling the RTOSes, and you assemble a complete system. At that point, it's possible that you might already have say a C code or an RTL or even an emulator that has some of this technology available. So the possibility of having to integrate all of them to create a single environment as well. So it really combines all of those together. So as you can see, a single environment is required to be able to do all of those. It does not make sense to do architecture or concept planning in one tool, hardware software partition tool, the post simulation tool, but rather you want a single environment that combines all of them together. Now, just like you saw the environment and you saw the different phases, architecture exploration is split into 4 parts. Model-based systems engineering, what they call ESL or most semiconductor, virtual prototyping, which is combining your hardware, software, and evaluating different attributes like functional safety as an example. And of course, doing a more hybrid model where if you already have pieces available, integrating them into the system. So it can be anything from a complete system, maybe a portion of a car that you might want to bring in, or it can be an ARM that's residing on an FPGA, or a piece of RTL for an SoC that might be on an emulation board. If I start off with model-based systems engineering, you can look at it where you can look at all the internals, so all the ECUs, the gateways, the networks that are within the car, but at the same time connecting to all the other external systems like Wi-Fi and the 5G and satellite communication, combines all of them into one model. Similarly, here if you look at a mission can be where I got a lot of aircraft, satellites, ground stations, and how do I build a network around it, all the way down to a data center. So today, a lot of the IoT systems or semiconductor vendors have to provide a solution, not just about what's inside of the chip or inside of the box, but also what is the performance when I communicate to a data center. So we're seeing a lot of IoT devices or even chips that go into IoT where they have to worry about message sizes and the rate at which messages are transferred to be efficiently utilizing that particular semiconductor component. So that is model-based systems engineering. So it can be done either very early in the design process, or that might be the actual design itself. Then you move on to the semiconductor piece, which is really about looking at it, not just semiconductor, but hardware and software, which is either I just want to design this artificial intelligence core, or I want to put an entire chip together, or I want to integrate multiple systems and boards together, or again, go to a network data center again and do the internals of the data center itself. You need different IPs to support all of these different pieces. But in a single design, if you're, say, designing a vacuum cleaner, for example, you might have IPs, you might be purchasing, you might be integrating it onto an FPGA or into an SoC, or you might have like multiple boards that might be distributed from the handle down to the duster bags. And you need to be able to integrate all of them in some sort of a network. And of course, the latest technology means that everything gets connected to a data center for collecting statistics or looking at the efficiency, or in some cases, even automating when the cleaning should happen. So we have a customer that's doing a vacuum cleaner that goes into a nuclear power plant. And one of the things they have to be worried about is once it goes inside, they don't really have a wireless communication. So they have to know what would be the maximum distance it can travel before the battery runs out. So once it goes, you can't come out. So, or once it gets caught inside, it's really hard to get it out. So you have to look at end-to-end every aspect to be able to get a really good quality product. Now, virtual prototyping is a concept that is kind of overused. Everybody uses a concept called virtual prototyping. So what does it really mean? Virtual prototyping is a terminology where you're taking something that might already exist in your system and you're trying to put that onto a new design. So it can be old software, or you can modify an old software to work on a new design, or you've decided on a design and you want to see for different types of applications or workloads what is going to be the, whether the diagnostics is sufficient to conform to the ISO settings, for example, or IEC settings, for example. Or it can be where, I want a platform where I can run my software and see what the functionality is. Is it doing all the right sequence of things in the software? And so here, for example, I can evaluate the performance improvement and power saving just from a software upgrade. So existing multi-core architecture, existing RTOS kernel, but then looking at, if I reorder my software, reschedule my software, can I get performance improvement? So for example, on an AutoSAR platform in a vehicle, we have seen where simple rescheduling can reduce your software usage by up to 35 to 40%. Now, one of the things that can be done is the same platform, the same system you have, can also be integrated with instruction set simulators to run your OS and your software such that you can do some early software simulations or even early software development. So for example, if the software is running and needs to connect to say, go to memory or go to a touch screen, is it enabling all of those correctly? Are all of those actions, all the opcodes, the expected value and expected results, are they doing it in the right order? Being able to capture all of those sensitivity of your system. And of course, the last one is looking at a variety of things related to security. It can be failures, redundancy, security, functional safety, all of those attributes. So looking at, and it can be at the node, chip, board, or even at an IP level, how this whole thing will operate. Or what would happen in the event of a failure. And of course, the last stage is what they call the hybrid prototyping, which is really about taking existing IP or RTL and connecting it onto a board or providing a design under test. So a major portion is on the hardware system, which is an emulator, for example, while your test environment, which can be a network or it can be the other boards on the system, are on the system level modeling environment, which is part of the architecture model. And then you can study, for example, the waveforms, or you can study what the expected response times are and things like that. As you can see, all of these are required in a product development flow. You can't just say, I'm going to do only one or the other. All of these are done either some of them may have higher priority and maybe spend more time on, while in other cases you might do one and then the other ones can be, just follow on as just kind of check marks or test cases. So, but all of these need to be available to say that you support artificial or architecture exploration. So what we're going to do now is take an example and walk you through how this would apply in a real system. So we've taken an infotainment system. The reason an infotainment system is very interesting is because of the fact that there are a lot of attributes that go into an infotainment system. You have a lot of sensors, you have gateways, you have different types of networks, you have wireless connections, plus you also have viewers, so like an infotainment system where you can view some data, you will have, it has to trigger certain operations, so you have displays, you have sensors, you have triggers, you have, like high priority responses which need to be taken care of, automatic mirror adjustments, all of those kind of things contribute towards the entire system working correctly. Now, let's stop here for a second and take a look at a particular design. So in this particular case, what we're looking at is an automobile. So we've got 3 networks connected gateways. There's a lot of different types of sensors. And we have the brake ECU, which uses a semiconductor component that is actually integrated with processors, security, memories, fault management, lock steps, and a variety of other features that require a lot of safety. So now what I'm going to do is move into VisualSim modeling environment, and we're just going to connect them all up here. So what you see here is a product called VisualSim Architect. VisualSim Architect is a modeling and simulation software that enables the entire breadth of architecture exploration. So what you have in this environment are libraries. So for example, if I click here, you can see a variety of libraries. You drag and drop components from the libraries, and each one of the library components has a unique set of parameters. You define the parameters values, and based on these values, that block will adapt to that type of functionality. And of course, you have a variety of parameters that you can utilize to try to run different types of trade-offs. Now I'm going to go ahead and run the simulation. Meantime, as I mentioned earlier, if anybody has any questions, feel free to ask those questions so that we can answer those immediately. They go through the chat window that you can ask any of these questions. Now, one of the things you can see here is as I'm running this model, there are a variety of statistics and a variety of plots that get displayed. Some of them are dynamic, some of them get stored in a file. So why is that? The reason is some of them you want to see interactively while the simulation is running, and others you want to see after the fact, like after everything is done. So for example, over here, I want to see over time what is the speed that the vehicle is moving at, and whether this was the expected and whether the outcome was also identical. So for example, you can notice over here, at this point, the road was icy, which was expected, but the mathematical calculations and based on the input data coming in from sensor, it looked like it's a pavement. So what you end up having is a safety issue where your original sensor was expected to say something, but after the processing, you ended up finding out that it assumed something else. So you have a risk right at that point. Now, you have processing, you have networks, and you have attenuators. So you have to make sure that they're within a deadline. So for example, here you can look at this. The re-braking starts off at a pretty high number where it takes about 1.6 milliseconds. But luckily over time, it starts leveling off and it gets to about 1.2. So you may want to look at why did I get that initial spike, which could potentially cause a problem in my particular design. So I've got to understand why that happened. And of course, then I can have, looking at, what's my latency on the processor, If I have any hardware components, looking at the DMAs, and of course here, when do the sensors arrive and when do I get incorrect data? It captures all of that type of information. So system modeling is expected to capture as much of the information as possible such that you can make very good decisions on exactly what your specification needs to be. So for example, here I've got the instantaneous power. What an instantaneous power tells me is over time, sorry, I've got the average power. So it tells me over time how much power is being consumed by this particular design. The reason that that is important is because this determines, what should be my battery capacity, how much should be my electric motor, how much time does it take to charge, all of those kind of attributes. And of course, you can get down to a variety of stats. For example, here I've got what's the fabric level. So these are the chip level stats. So some of these like the vehicle functionality, this is the total system power, this is like interfaces from the sensors to like here down at the chip level. So you can get any number of statistics that might be valuable for your particular decision. Now, so this is at the network level. Now, what you can do, excuse me, what you can do is you can say, okay, now based on that whole overall simulation, I just want to focus on one attribute, which is I want to see CAN and Ethernet come into an FC bus, and I've got some CPU, GPU, display controllers, DRAM, and display I/O. Now, what I can do is build a system model that focuses on only that attribute. You saw the earlier one for the entire system, but here I'm just going to focus on this one attribute and see what the behavior is for that one attribute. So what is that really? You notice here I've got my Ethernet, CAN, ARM, GPU, and display. But what's important is the variety of parameters that I can tweak to do trade-offs. So for example, what is the rate at which the data is arriving from CAN Ethernet? What is the data size? What's the request from the ARMs, both reads and writes, and also from the GPU, displays, and then of course attributes of the bus as well. Why are you doing it at this level? This is the process where either you have to determine do I need any accelerators, or to determine how much of the of the functionality can be done with say an off-the-shelf chip, or how much of functionality can be done by off-the-shelf IPs that I can integrate into an SoC. So this is my starting point. So when I get started with something like this, what I see over here when I look at these are all of these are essentially traffic generators. So I've got like this is the read rate, and over here I specify what the data attributes are for that ARM. So when I go ahead and run a simulation, here I get, for example, what was the bus latency. Here I get the traffic timing plots. So that's my Ethernet, my CAN, ARM. What is happening over time. You can see, which one's the busiest. As you can see here, the GPU is really the really busy one. Here's the thing that's very interesting, which is my latencies for my different parts of my system. So for example, the GPU latency, the ARM, the Ethernet blocks, you can see the black lines going over here, the CAN. So over time, you can see what is the latency for each one of these interfaces to look at, where is going to be my potential bottleneck. For example, right here, you can see this amount of time it takes for a display controller. Now, you have to understand, why is it taking so long for a display controller to do that? Is that the requirement, or is it something that because I have a host of other activity going on right at that point? For example, you can see all the ARMs are busy. You can see the GPU is busy. I have a CAN Ethernet activity, and then I also have the display controller. So is that the reason why it's going down, or because the processing it is expected to be at like 1 1 microsecond as opposed to all the others which are in hundreds of nanoseconds. So allows me to understand where is going to be that bottleneck. What is this performance requirement or maximum performance I can get out of my system? So once I understand at this level of granularity, then what I can do is I can start putting in more detail inside. You know what? I'm really going to go get an off-the-shelf chip. So, and then, for my interface, for my camera, I'm going to go store it outside and go through a PCIe to a DRAM, the update. So then here's my details of my cameras, the GPU, and all the other devices. This is my starting overview of what my system is going to be doing. Now, what is interesting about this particular design is the fact that now it's no longer just a single chip. For example, here, I have a decision. Do I go with the NXP or do I go with an NVIDIA chip? But now I also have to worry about, I need a PCIe interface. I need to put a vertex because I need to do some data processing and storing on a memory map for my video data. Then I need a DMA that takes it close to the PCIe to the DRAM. And then, how many cores do I need so that I can get the performance? How many threads or processing engines do I need on my GPU? Being able to look at all of those kind of requirements. So when I do that, I'm going to go ahead and run a simulation of this thing where I have now a different set of parameters. You remember earlier, our focus was really on the, what's the data rate, what's the data size? But no, you have what's the cache loading, the bus bursts, number of packets, what's the graphics traffic rate, the frame times. So now the performance or the requirements is being narrowed down based on the high level, concept level system model, where now I know these are the things that require, so I can start putting in more of the fine granularity of my particular design. So if I go in here, for example, remember the earlier one was just a traffic generator. Here, I now have ARM processors. It's no longer just a graphic or a delay block. I actually have inserted a processor in here. And of course, DMAs, and now I'm starting to insert things that are far more detailed or accurate than what the earlier set of models were doing. And as you can see now, I can start putting like an AXI bus with details that you wouldn't do at the system level, like thresholds and the arbitration schemes and things like that. So now when I look at it, now I'm getting a completely different set. So here I'm focusing on, for each of the warps or threads, what's my latency? And now I'm going down to that level of detail. What is the MIPS on my processor? What's the power, both the average and the instant power? So now we're looking at not just the average power, but also the instant power. Why is that important? The reason that is important is because that helps me figure out, is there ways I could offset some of these stats? So if I go in here, you can see it's almost about 7 watts of power. Like down here, 24.5. So I have almost like a 40% higher power. Now, if I could push that down a little, I could be saving a lot of thermal cost because my cooling cost would go down. Also, you can see my display control. You can understand why it keeps going up and down by a huge range, and you can also understand why that is happening on the the earlier system model. If you remember, that was the one that was right on top there. So now that you have understood how your system behaves, you now have the ability to start saying, okay, now I can start optimizing each of these definitions, change parameters, run simulations. So for example, say I increase this to say about 100 packets, and now rerun. How does that impact my overall system? Does my latency change? Now, power seems to be okay, but let's look at the latency and see if I'm, the latency is increasing. Because remember, no matter what, all of these have to hit the memory. You've got to run it for a little bit. Now, one of the things you're going to notice here is only 256 threads are running. So I'm actually not running the second set over here. And the reason I'm not running it is because I just got one program that I'm focusing on my GPU. So only that program alone has been configured. The others have not been configured. So you notice here, interface latency is up a little bit, but not significant. So now what I'm going to do is I'm going to get ambitious. So you know what? Let me do 300 packets. Let's see what happens there now. So this is the packets coming in from the video interface. Remember, this is on a network video interface. So we can start seeing whether we're going to get the same performance, or is the performance going to be much worse. So as I keep increasing it, you can start seeing the activity that is going on in my particular design, and starting to see if my latency is increasing. So you can see even at this level, my latency hasn't really changed. It's still about the same, which means no, I can't. So what I noticed is the DMA over here, you can see the red thing around here, tells me that I'm out of buffer capacity. So that tells me that even though I can send more data into my context, because of my bottleneck, either the PCIe or AXI, I can't really run the system, and I'm having a bottleneck. So this tells me there are two ways. I can increase the DMA activity, or I can, for example, increase the number outstanding. So I can say, like, let 10 of these go through at the same time, and we can run that and see if we're going to run it for a little bit. Is it going to run for a little bit longer, or is it going to fail right away? So what you're doing is you're starting to do trade-off studies to really understand what is happening in my design, to really explore where I'm going to potentially have a bottleneck or potentially have a problem. As you can see now that I've made more of these parallelization, I'm actually able to run a little more, but again, it looks like it's a band-aid. It's not a fix. So I really have to change other things. So then I have to look at, do I change the PCIe? Do I change the AXI bus? What do I change to get better performance? Now, shall I move this into round robin here, as opposed to running on one of them getting higher priority? What happens to my system? So this way I can start doing explorations to figure out where my problem is, and at the same time also do power performance trade-offs. Because I got my power, other ways I can reduce my power as well. So looking at that aspect also of my particular design. So that's the system you saw here. You can see a discrete DMA. So these are components on the board. This is a chip that we're purchasing, and then of course you got external DRAM. These are the library blocks. This is done in a software called VisualSim Architect. And these are some of the standard library components that are available in the product that I use for this particular design. There's a variety of trade-offs that you can look at right over here. Some of the experiments also provided in this thing over here as well. Now, we started off from a networking level, looked at an overall system, granulated it down to selecting IPs and selecting components. Remember that it's not just the engineering team within a company that's doing this. This is something that you can share with your customers, and they could be integrating their full system and seeing how this whole system will work. So it also becomes a way to communicate across the companies and also across customers that you might have that need to start doing this type of work. So here, for example, we're focusing only on one aspect, which is the AI component of this overall system. As you can see over here, you have a host coming into a TPU. You can see it comes into a PCIe. There's a weighted 5-4 unified buffer, matrix multiply, accumulate, and activate. And you can see for the matrix multiplier, what is my latency and what's the TPU overall latency. So you can use this to figure out if there are ways I can modify the flows of these different, either functionality or increase the memory capacity. See what happens. So not only can you do it network level, a bunch of boards, chip, but also at a single IP level that you can do. And architecture exploration means you should be able to support all of them, because someone either within your organization or extended organization, your customer, would have a need for one of these. So having all of it is an absolute requirement. As I mentioned earlier, there is a chat window. You can go ahead and ask the questions in the chat window, and there will be people that are available to answer these questions. Now, system level power evaluation. Remember, we spoke about power, functionality, and performance, which is throughput and latency and utilization and efficiency. Power is something that is always ignored at the architecture level. The reason is there isn't enough of information to be able to do an efficient power model. So a lot of times people end up using Excel spreadsheets to do power. Unfortunately, the analytical model is a good starting point, but unfortunately, the analytical model tends to have a lot of limitation. And the limitation is because they do not have the key information, which is the workload and the traffic. So what is the application doing, and what is the traffic, like the interfaces and things like coming into the design. So here, for example, you can see that the instantaneous power starts off at this level and keeps going up. Now, why are these different points at the same cycle critical? That indicates how many devices are turned on, turned off. So if you're trying to do offsets, the instant power tells you which device I can turn on and turn off, and that way, I can then shift some of the power to a lower position, so that way I get, like more efficient. Or I do some sort of a power management. So for example, I'm going to run a different model. So this one here, for example, focuses just on the semiconductor component. I have a couple of behaviors. One is a phone, the other one is more of an MPEG video processing. So I'm going to go ahead and run it where everything is initially running on the ARM subsystem. So there's no other, really accelerator or anything like that. I'm going to see two things. One is, how many frames per second or how many matrices per second I can manage. And the second one is looking at the overall, the average power. That's the instantaneous power, and the average power. So I was typed incorrectly. So you can see that our goal here in this particular design was to try to get it below 1 watt of power, but then get to about 23,000 frames or matrices per second. Right now, we're good on this one. We're sub 1 watt of power. You can see, which device is taking what percentage of the power. Unfortunately, the performance here is only 14,000 matrices per second. We really want 23. So what we're going to do now is we're going to go back to the model. We're going to look at this and say, okay, this one is a candidate based on other data that I generated. It's a candidate for doing a hardware accelerator. Can be an FPGA, can be in the chip, can be any combination. So I move that to hardware, which means we're going to be running on this component here as opposed to this component there. And now we're going to take a look and see what the performance ends up being. Okay, so now what you're seeing is earlier on, if you notice, it was just down here, the idle wasn't doing anything. And you can start seeing the spikes. It's actually more than a spike, it's actually quite a bit of processing in the hardware. This is the hardware accelerator. You can see it starts spiking. I can even put dots to see what it looks like. You can see it keeps going up and down. And here's the most important thing, how many frames. And I get about 27,000 frames. 23,000 was my goal. I'm over that, so now I'm happy. But the power here is shot to over 1.6. So I've got almost a 60% increase in power. Can be very good. And you can see here my spikes are much higher. So now what I want to do is go back into the model, and I'm going to enable power management for the hardware engine. So what my logic is if it's in standby for more than 1 millisecond, move it to idle. So that's just one power thing that I'm doing. I could be doing a variety of power, like I could have a more complex state machine, I could do an expression-based, any of those. But in this case, for the purpose of demo, this shows up much better. So now we're going to be looking at what is really happening in my particular design and trying to understand what is going on here. So now if you notice, spikes up. Earlier on was staying at 0.2, but now because we're moving into idle state, it drops. So most of the time it's actually sitting in idle state, so which means our 1.6 has dropped off to approximately 1 watt of power, which is our goal. Performance-wise, a little bit of a dip. You can't really see it here because the number is huge, but it's not significant to say, okay, this is going to cause a performance issue. And of course, you can see the peak power as well to take a look at. But the main thing is now I was able to move one of the functions to hardware acceleration and then also do some power management to get back some of the power that I had lost. So allows me to do a variety of trade-offs. That way I can actually see what the, two things. One is I can see what the system is doing. And the second aspect is I can see what the, what can be done to enable it to meet enable the specification to meet the requirement. Now, one of the attributes that you also require at the system level is the ability to see a timing diagram. And the reason for that is to be able to see, the state change over time. Is it like mostly, if I look at this, I see a lot of activity happening at regular intervals in all the memory devices. So it's like 32 memory devices. All of them have significant memory activity. But then I also see significant time periods of where wire power or even some of these memories are inactive or in standby mode right here. So you can look at that impact as well. So timing diagram is a nice thing to see, like where am I busy, where I'm not busy, how could I improve that capability, things like that. Okay. Now, one of the aspects that is left out in almost all architecture exploration is reviews such as redundancy, reliability, efficiency, failures, functional safety, all of those. And it's not just a question of saying, okay, I ran the model and this is the result I got and no, it didn't meet it, but rather, what is the scenario that I really want to see the performance? So for example, you saw the thing where the road condition sense sent data where it was processing it incorrectly. So you want to be able to capture those. Those are part of my failure study. Like what happens if one of the codes fail? Or for example, in my software task diagram, I have it where I need these semaphores, but to release the semaphores, I need this one to complete. So I've got kind of a deadlock. Being able to evaluate all of that at the system level is kind of critical. So what you saw here is a variety of designs, starting from a high network to like a distributed system, to semiconductors, to IP, and finally looking at power and failure analysis. Again, one of the key things is everything should be done within the same environment. Now, one of the things that provided here is is a variety of videos that are available that you can take a look at to help you learn more about each one of these topics. A quick introduction to Mirabilis design VisualSim. We've been around since 2003, but really the activity started in 2008. And we're now responsible for over 250 products worldwide. And one of the key things we're going into is virtual prototyping, which is taking instructions and simulators, running software on top of it, and running it in the context of the entire system. So this is something that is new, and it really provides us a complete end-to-end solution. just a sampling of some of the companies that use VisualSim in the design of their products. Now, Mirabilis Design provides the products in three formats. You can either just buy the software with the libraries and build everything yourself. We can provide you the training, or we can actually build models or subcomponents either way the user wants and provide it to you, and you can be responsible just for integration and analysis. So there are both mechanisms available right over here. So VisualSim is the demo product I was showing you all this while. You can do a variety of things: timing, throughput, power related, looking at end-to-end simulation of my entire electrical engineering system or my entire semiconductor, and then functional and safety analysis. So things like, like providing libraries to enable you to assemble all these systems very quickly, especially when it comes to hardware, software, and network. So you can really understand what are the resource requirements for each task in the application task graph. And of course, you can put checks and balances, and that's where the functional safety comes in, where you can see whether my diagnostics are responding within a certain period of time, or, for example, if I've upgraded PCB, is the channel reliable enough to be able to handle the PCB workload, or is my channel too noisy? So I've got to evaluate my channel as well. VisualSim has a huge library of components, and the reason that this is important is because the libraries are the reason that you can accelerate your product development, product evaluation, and studies, trade-off studies. Now, the reason VisualSim is used and is probably the #1 product in the system design space is the four following reasons. One is the size of the library. Any application you take and any level of abstraction, you have a library for that. There's a huge spectrum of analysis and studies and trade-offs that you can do. It's probably the broadest in the market. Now, because we provide you a large number of reference designs, ease of use, libraries, we can cut short your development time, sometimes by even like 6 to 9 months of your development cycle can be reduced, shortcutted by this approach. And of course, one of the other things that I stressed on as being very important part of architectural exploration is the fact that you want to be able to have concept, marketing, communication, engineering, field testing, customers, all of them, or even your suppliers, all of them being able to run off the same platform. Not exactly the same license, but rather they could be on their regular systems, but have the ability to be able to import and export from those designs without having to make any changes or go through process or none of those kind of things. So on the profit taking, one of the things that a tool like Mirabilis Design brings to architecture exploration is really the acceleration of model creation and the analysis. The analysis is important because when you have to do some rework or you have to do some bug fixes during development or integration, you lose a lot of time. Plus, you have to do patchwork. When you do patchwork, what ends up happening is you end up creating problems in other parts of the design. With the VisualSim methodology, since you're doing all of that before your implementation, you get the highest quality product, which allows you to gain a lot of time, significant amount of time in your product schedule. Some of them we've seen is upward of 30, 25%, or 1/4 of your schedule. So if you have a 2 or 3 year project, you have the ability to significantly increase it. With this, I would like to thank all of you on attending this presentation. I'm now available to answer any questions. Feel free to ask them, and I'd love to be able to talk to you now or sometime later.